Hello friends, in this video today we are going to discuss about Fresnel's biprism. Okay, and here you can see the diagram. So the Fresnel's biprism, you can consider this is a prism that consists of two prisms, okay, like that, and you can see the refractions by the upper half and lower half as shown in the diagram, right? And you can compare this its theory can be compared with the Young's double slit experiment. Okay, I will come to this later. Okay, first let me tell you something that in this video I'm going to show you how to determine the wavelength. Using Fresnel's biprism, and how to determine the thickness of a transparent sheet when it is placed in the path of the light. Okay, thickness of sheet. Okay, so we are going to discuss these two topics in this video. Okay, so now let me clean these things. Okay, just wait. So here this S is a source of light, which is a monochromatic source of light. Now you can see light from this source is going to upper half, is reflected in these two directions, as you can see, and by the lower half it is reflected in these two directions. Okay, and due to after refraction, so we can see the fringes here on the screen. Okay, dark and bright fringes. Okay, and here at O we're gonna get the central light. Okay, now here you see as it reflect this way, then you can see if you draw dotted line here. Okay, if you draw dotted line here, then these 2 points again here also, if you draw dotted lines, these 2 points S1 and S2, these two will appear as virtual source of light, right? Let me draw it properly. Just wait, just give me a second. Okay, so this is S1 and this is S2. Okay, so these two will appear as virtual source. Okay, now you see, let me consider that distance between these two S1 and S2 is suppose small d. Distance between the two sources, virtual sources S1 and S2, suppose let it be small d, not capital D, and the distance from these sources to the screen, let it be capital D. Okay, this distance is suppose capital D. Okay, and in that case you can compare with this with the Young's double slit experiment with this setup, right? Here these two sources are there. Here we are going to get the bright dark fringes. Okay, so if you have studied the Young's double slit experiment in senior secondary level, here fringe width is given by beta is equal to lambda capital D by small d, right? And from here we can obtain wavelength, that is lambda is equal to beta d by capital D. If you know the values of capital D, small d, and the fringe width beta, then you can determine the wavelength. Okay, now let me write the theory here and meaning of the symbols, and let me paste a proper diagram. Okay, let me paste a proper diagram here. Just give me a second. So here you can see the light falls on the upper part of this prism. Upper part on this prism is refracted downward like this. Okay, and the light falls on the lower part of the prism, refracted upward like this. Okay, And so interference, you can see the interference on a screen if you place here, and you see after refraction you can see that clearly. So when this light falls on upper part of this prism and refracted downward, okay, refracted downward, then a virtual image of the source S is formed, which is S1. Similarly, when the light falls on the lower part refracted upward, and this S2, which is the again virtual image of S, is formed. And so we can consider this S1 and S2 are virtual monochromatic source. And if we consider that way, then we can compare this with Young's double slit experiment. Okay, so let me go to a new slide. So you can compare this with this Young's double slit experiment. Okay, here O is the position of the suppose central bright fringe, and this is suppose small d, and this distance is capital D. Okay, right. So here we're gonna write that so we can say that the theory of interference and fringe formation in case of Fresnel's biprism is same as Young's double slit experiment, same as Young's double slit experiment, right? So that means here you see, as the point O is equidistant from S1 and S2, from the sources S1 and S2. Okay, this point. Okay, so the central bright fringe of the maximum intensity, the central bright fringe of maximum intensity occurs at O, right? So on the both side of O, alternate bright and dark fringes will occur. Okay, on the both side of O, on the both sides of O, alternate bright and dark fringes occurs. Right? So hope you have understood this. The width of the dark fringe or bright fringe is given by the width of dark or bright fringe is given by beta is equal to lambda capital D small d, right? So we have got this fringe width in Young's double slit experiment. Okay, so because the theory is same as Young's double slit experiment, so we can use the same relation here as well. Okay, so hope you have understood this. So here this capital D is the distance between the source S. If you go to the Fresnel's biprism, this S, and distance between O is capital D, right? That means sum of two distances, these two distances A plus B, right? So hope you have understood this. Okay, and small d is the distance between S1 and S2, which are the virtual sources. Distance between distance between S1 and S2. Okay, so from here we can determine the wavelength. Lambda is equal to beta d by capital D. So this is the formula. This is how we can calculate the wavelength, right? Using this Fresnel Biprism. Okay, so you see here, using this relation, we can determine, right, wavelength of light, right? Hope you have understood this. And if you don't know the theory of the Young's double slit experiment, and if you want me to create a video on this topic, then you can let me know. You please do let me know in the comment box. Okay, so now let's move on to the next topic, that how to determine the thickness of a sheet which is placed in the path of light. Okay, let me show that one. So now let me explain how to obtain the thickness of a sheet of transparent material when it is placed in the path of in the path of one beam of light. Then the central bright will shift to another position. Let it be suppose this position P. Okay, it's shifted to P when the when a thin sheet of transparent medium is placed in the path of a beam. Okay, its thickness is suppose T, small t. Let me take that way. Okay, now you see, suppose a transparent sheet of thickness T and refractive index mu, suppose refractive index mu is introduced in the path of one of the beams. Okay, so due to which this central bright shifted to P. Okay, central bright fringe shift to P, right? Now the light waves from S1 to P, this light wave, so partly travel in air, then in the thin sheet, then again in air, right? So now distance travel in air by the wave from S1 to P is S1P minus T. T is the thickness of the transparent sheet. So this is the complete part, and out of that this part is the thickness. So this portion is air. So total, from the total part, so if you subtract T, that will be the distance covered in air, right? So we have understood this. And in the sheet, distance covered in the sheet, that means through the sheet, is T. Okay, so optical part, so let me write del S1P is S1P, that is travel in air, S1P into T plus, and this optical part through the sheet is mu into T. Here mu is the refractive index of the sheet. Now you see, so thickness of sheet is T. So you may think that distance through the sheet must be T. Actually the distance and optical distance, two different things. Let me explain why. Let me take a new slide to explain this. Okay, now you see, suppose we have a medium. This is the medium. Okay, this is the thickness, suppose T. Now you see a optical path of length indicates the number of light waves that fit into the path. If this is the path, okay, then how many number of waves fit into this path, that is the optical path. That means you can say optical path is given by del n into lambda. N is the integer, that means integral multiple of lambda. Optical path is always integral multiple of lambda. How many how many waves fit into this path. Okay, now you see, if the wave travels through this medium with velocity suppose v, and its thickness is t, then the distance covered instead of this t, let me take this thickness is suppose L, because I'm going to use the t for time. Okay, so it takes, or you may take, okay, let me keep this thickness is t. T is not time here, thickness suppose, and let me take time taken to cover this thickness is suppose tau. Okay, then tau is equal to v into t, right? So because you see that this speed of light through this medium, that will be given by distance is equal to the thickness of this slab by the time. So that's why you see this thickness t will be equal to v into tau, right? And you see the distance traveled by light in a vacuum in the same time tau, distance traveled by light in a vacuum, in a vacuum light, speed of light is c. Okay, speed of light is c, right? So therefore distance is equal to speed into time. So distance travel in vacuum is c into tau. We can write c into tau. Okay, now you see that this tau can be replaced by this relation, tau is equal to t by v, right? If you replace this tau by t by v, here c by v gives you the refractive index of this medium. So c is the speed of light in vacuum and v is the speed of light in the medium, so that is mu into t. That's how we have got that optical path through the slit is mu t, right? Hope you have understood this. And now let me simplify this. On simplifying this, what are we gonna have? So we can write S1p and we can take mu common, t common from these two terms. Okay, so here we're gonna get mu minus t, right? Mu minus, not t, 1, mu minus 1. If you open this bracket, then from these two terms you can take t common, right? Hope you have understood this. Now you see an optical path covered by this wave from S2 to P, del S2 P is simply S2P, right? Now optical path difference between these two, the optical path difference that will be given by del S1P minus S2P. Now you see, as I have said that on putting this sheet, this central bright is shifted to P. That's why the optical path must be equal, okay, at the central bright. Okay, so that must be equal to 0. Now from these two results, what we will get on the left hand side. Okay, let's use these two results here on the left hand side. Okay, then what we're gonna get, so let me take a new slide. Okay, let me copy this. Just wait. So here is the last relation we have got, and we have let me copy this two as well. So here you can see, let me use these two results here. What we're gonna get, S1p plus t mu minus 1 minus this is equal to simply S2p, and that's is equal to 0 on the right hand side, right? Now from here you see what we can write, S1p minus S2p is equal to, that's gonna be here you see, just let me write this way, S2p minus S1p then t minus mu 1. Okay, so I have shifted these two terms on the other side. Okay, hope you have understood. I have made this S2p positive, okay, on the other side, right? Hope you have understood this. So now you see, consider this, let me go back to the diagram. Here you see, if you consider this is equal to x, okay, this is equal to x, that means if you consider the the lateral shift of the central bright, so let me write, let me mention here, if x is equal to the lateral shift of central bright, central bright, that is OP, then what we can write this, now you see, let me explain. So let me go back to the diagram. Here you see, if you consider, so as we have taken this distance is capital D, right? This distance is capital D, and this portion is small d by 2, because distance between S1 and S2 is small d, that's what we have taken. Now you see, if you draw a perpendicular here, so this is suppose S1n, right? So then what you can write here, you see, now you suppose draw a line here, sorry, if you draw a line, this is the point, suppose this point is suppose E, and let me draw another line here, okay, this point is suppose F, so this gap is d by 2, right? D by 2, this is also small d by 2, right? Now here you see what we can do, that we can write here, we can we got two triangles here, you see, one is this, okay, and another triangle is this, okay. Now let me go to new slide. So here you see we have got two triangles, one is S1PE, another is, you can see this is S2PF, okay, another is S2PF, S2PF. Now you see this portion clearly, as this part is x and this part is d by 2, so that's why this portion must be x minus d by 2. Hope you can you understood this, right? Okay, you see this portion is x, and this portion we need to find this portion, and this portion is d by 2, and whole part is x, so this remaining part must be x minus d by 2, right? So that's why we can write this portion is x minus d by 2, and this is capital D, obviously capital D, and similarly this is also capital D, and this part PF, now here you can see this part is x, then this part is d by 2, so that's why this whole side PF is x plus d by 2. So this is x plus d by 2. Now you see we don't need this perpendicular SN now, just wait, we don't need this. Okay, now you see from triangle S1PE what we get, that S1P whole square, if you apply the Pythagoras theorem, d square plus x minus d by 2 whole square. On the other side, from triangle S to PF, from S to PF we get S to P whole square d square plus x plus d by 2 whole square. That's what we're gonna get. Now let us find this part. That means S2P minus S1P. First let us take square of this two. Okay, then you have to subtract these two, right? Then what you will get, that let's put the right hand side as well. Then we have got this relation, right? Now you see here d square cancel. Because of this minus, this sign will be also minus actually, right? So then if you simplify this on the right hand side, that x square plus 2 into x into d by 2 cancels, again d square by 4, then minus x square minus 2 into x into d by 2, then plus d square by 4, but there is minus sign, sorry, not this one, there is minus sign, so this minus will be plus and this plus will be minus here, and here you can see these two cancels, and here plus d square by 4 and minus d square by 4 cancels, right? Hope you have understood this. So x square minus x square gone, so we have only x into d, x into d. So we have got S2P square minus S1P square is equal to x into d. So we have got 2x into this is plus, this is also plus, x into d. On the left hand, on the right hand side we have got xd plus xd, right? So that's why it becomes 2xd. So S2P, it can be written this way, S1P into S2P minus S1P, applying a plus b into a minus b, right? So now S2P minus S1P, that's gonna be equal to twice xd by S2 plus S1P, right? Okay, let me tell you one more thing. In this setup, as you can see in the diagram, in this setup, so this S2P, the length of S2P and S1P and D, okay, they are not differ by very large margin. Okay, so that's why we can approximate S1P S2P approximately equal to D. Okay, approximately equal to D. If that is the case, then we can write this plus this is equal to twice D, right? Therefore S2P minus S1P is equal to twice xd by, here we can write twice d, here 2 cancels, so we have got x small d by capital D. So now you see, let me take this as suppose equation number 1, and using this equation number 1, let me use this result in this equation here. Then what we will get, let me copy this equation. So this was the equation number 1. Now so S2P minus S1P, if we use this, then what we're gonna get, T mu minus 1 into x small d by capital D using 1. So therefore the thickness of the T is equal to is given by, if you simplify this, x small d by capital D into mu minus 1. So this is the thickness. thickness of the transparent sheet of the transparent sheet. So hope you have understood this. Thank you for watching. See you in the next video. Bye bye.